Learn like a pro.
Have you ever stopped to think about what a distant star, a single living cell, and the device you're watching this on right now all have in common? It sounds like a trick question, right? But they're all built from the exact same universal blueprint, a fundamental set of instructions that shapes literally everything.
So today we're going to pull back the curtain on that master plan. How do just a handful of simple, basic particles manage to build the incredible complexity we see all around us? Well, let's find out.
Here's our game plan. We're going to start by building an atom from the ground up, then meet its key players. After that, we'll see what happens when you start messing with the recipe a little bit. And finally, we'll discover how this simple blueprint gives birth to one of the most powerful forces in nature, radioactivity.
Okay, first things first. Every single atom, it doesn't matter if it's hydrogen or uranium, is organized into two very distinct regions, and each one has a supercritical job to do.
Think of the nucleus like the city center. It's incredibly dense and heavy, and it's where pretty much all of the atom's mass is packed in. And those electron shells? Well, they're like the sprawling suburbs, defining the atom's size and, more importantly, how it interacts and socializes with all the other atoms out there.
So, what are these regions actually made of? Let's meet the three construction workers of the universe: the proton, the neutron, and the electron.
And here's the dashboard with all their vital stats. You can see protons are positive, electrons are negative, and neutrons, well, they're neutral. Protons and neutrons live together in the nucleus, while those electrons are just zipping around on the outside. Seems pretty straightforward, right? But one of these stats completely changes the game.
It's this one, this tiny little fraction right here. It might not look like much, but this number shows the absolutely massive difference in weight between the particles. And it's the key to understanding, well, pretty much everything about an atom's mass.
What this means is that an atom's weight is almost entirely concentrated in that tiny central nucleus. The electrons are totally essential for chemistry, but when it comes to weight, they're basically just noise. They add practically nothing to the scale.
And this is the secret to a happy, stable atom. You see, nature absolutely loves balance. The positive charge from all the protons in the nucleus gets perfectly canceled out by the negative charge from all the orbiting electrons. The result? A perfectly neutral atom with no overall charge.
Now, to keep all of this straight, scientists came up with a handy little code. The big X is just the symbol for the element. The bottom number, Z, is the atomic number. That's the proton count, and it's what gives an atom its identity. The top number, A, is the mass number. That's the total number of protons and neutrons combined.
Okay, let's put it to the test. Here's vanadium-51. The bottom number, 23, tells us right away it has 23 protons. Now, because a neutral atom needs to be balanced, it must also have 23 electrons. Simple enough. To find the neutrons, we just subtract the protons from the total mass. 51 minus 23 leaves us with 28 neutrons. See? Easy, right?
Okay, so we've got our rules set. The proton number defines the element, and it has to be balanced by electrons. But there's one part of this atomic blueprint that has a little bit of wiggle room: the number of neutrons.
And this little loophole introduces something fascinating called isotopes. The best way to think about them is like different models of the same car. They're all the same make, but some are just a little bit heavier. Maybe they have a bigger engine or some extra features.
Just look at these two cores. See how they both have the same number of those cyan-colored protons? That means they are the same element, period. But notice core 2 has a couple of extra gray neutrons packed in there. That makes it heavier, and that one simple difference is what makes it an isotope.
Chlorine is a perfect example of this in the real world. You have chlorine-35 and chlorine-37. Both have 17 protons, both have 17 electrons, but look at the neutrons. Chlorine-37 has 2 extra, which pushes its total mass up from 35 to 37.
So what's the big takeaway here? Well, since the number of electrons is the same, these isotopes act pretty much identically in chemical reactions. But that difference in mass gives them unique physical properties. And that's a really big deal. It's what lets us do things like carbon dating or use special isotopes in medical scans.
So we know the number of neutrons can change, but what happens when that change goes too far? What happens when you try to stuff way too many or maybe even too few neutrons into that tiny nucleus and completely throw off that delicate balance?
And this image just nails that tipping point. On the left, you've got a happy, stable nucleus. All the forces are in harmony. But on the right, that nucleus is unstable. It's buzzing with excess energy. The forces are all out of whack, and the whole thing is basically ready to fly apart.
And there you have it. That's the origin story of radioactivity. It's not some weird, mysterious force. It's just an internal imbalance inside an atom's core. An isotope with an unstable nucleus is, by definition, a radioactive isotope.
But here's the thing. An unstable nucleus isn't just going to sit there being all chaotic. It has a fundamental need to get back to a stable, lower energy state. And to do that, it's got to ditch that extra energy.
So, the nucleus finds its balance by literally throwing stuff out, energy and particles. We call this whole process radioactive decay, and the stuff it ejects is what we call nuclear radiation, which usually comes in the form of alpha particles, beta particles, or high-energy gamma rays.
And honestly, this quote just says it all. The entire incredible phenomenon of radioactivity, from nuclear power plants to life-saving cancer treatments, is all driven by this one simple, fundamental quest for stability inside the atom.
So we've decoded the atomic blueprint. We know how it's built, and we know what makes it break. But this just opens up an even bigger question. This atomic rebalancing act unleashes a colossal amount of energy. So how have we, as a species, learned to control and harness a fundamental process that's been written into the fabric of the universe since the very beginning?